Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation FET, a physics perspective. This is lecture number 6 and we will be now explaining to you the various facets of MOS capacitor and its defects. Now let us start. We have already seen in our previous discussions when we were discussing threshold voltages and when we were discussing charges in the MOS capacitor as a two terminal device that typically there are large number of defects at the silicon dioxide interface, right, and these are primarily because of fabrication issues, because of instability while you are doing a fabrication or some impurities getting inserted during any process while fabrication. So there can be interface trap charges available, there can be oxide trap charges which can be available, and when these trap charges are available, what actually happens is, from a very first principle point of view, the electric lines of forces which need to terminate at the silicon dioxide interface or just near the silicon actually terminates well ahead of it. So the flux actually reduces onto the silicon surface, right. What does it affect? This causes a shift in the flatband voltage, and therefore when the flatband voltage changes, you very well know that the threshold voltage will also change, right. It also affects the capacitance versus voltage characteristics. Do not worry at this stage from where this is coming, but it will change, and how it will change you will see later on, right, which means that three things will happen primarily when you have defects in a MOS capacitor. If I have a MOS capacitor which is defect free and I am comparing that with a MOS capacitor with defect, there will be shifts in threshold voltage, flatband and the capacitance, right. So these three things you should keep in mind as far as these defects are concerned. Now there are typically four types of defects which are available with us. The first type of defect is the mobile oxide charge, right. The second is an oxide trap charge, the third is a fixed oxide trap charge, and the fourth one is an interface trap charge, also referred to as a fast surface state charges. What is a mobile oxide charge? I will tell you what happens. When you are actually doing an oxidation, you use a wet oxidation methodology, which means that in order to enhance the speed of the oxidation, you might use a humid atmosphere or you might use water to do it, distilled water. There you have impurities like sodium, potassium, ions available, and these are very small ions which can be inserted while you are growing the process, and they will generate what is known as a mobile oxide charge. And these are mobile oxide charge primarily mean that if you apply a bias now, they will actually start moving, right. You will ask me why is this so important, why being mobility or immobility is an important part, because if your mobile oxide charges by application of external potential starts to move near the silicon dioxide interface, right, the effective flatband will change, right. That is the reason mobility or immobility of charge carriers are important. So if you remember, I had silicon double bond O as my silicon dioxide, right, silicon double bond O. I will have silicon double bond O and now let us suppose while fabricating or while doing it, this silicon double bond O is okay on side, but these two are not being bounded. So these are sort of open sort of traps. So this is an oxide trap charge. What is a fixed oxide trap? Fixed oxide trap is due to the structural defect within the oxide layer. And finally we have an interface trap. Interface is that at the silicon dioxide interface. So this is what is referred to as silicon dioxide interface also. That means I have my silicon which is basically an unfulfilled silicon. The silicon is not being fulfilled and you have dangling bonds available here. This is the interface trap charges. What are oxide trap charges? Oxide trap charges are due to electrons or holes which are trapped in the bulk of the oxide, right. It is not an interface phenomena, but it is trapped in the bulk of the oxide and it is basically immobile. So you have fixed oxide traps, you have oxide trap charges, you have interface trap charges which are available with you. These four types of charges will affect your VFB and finally your phi ms and therefore your threshold voltage. These defects, and these defect to a larger, for example, mobile oxide charge does not depend upon doping, it does not depend upon temperature, it does not depend upon many factors, right. It depends mainly on the type of fabrication principles which you are applying, right. Similarly, if you take up let us say fixed interface trap charges. It also depends upon the nature of silicon which is there and how oxidation is forming with respect to silicon, that will be basically inbuilt within the oxide layer. So, these things you should be pretty careful about as while explaining the defects. Now, as I discussed with you, these 4 1 2 3 4 are the trap charges, and therefore, this look at this FVB. If you look, FVB is given by phi ms minus q naught prime by Cox prime. We have already done this point, I will not further repeat this. Q naught prime is the effective interface trap charges per unit area, and Cox prime is the oxide capacitance per unit area which you get, and that is given by the VFB. So, you see, higher the value of your Q naught prime, which is the effective interface trap charges, right, smaller will be the value of VFB, which is shown on the here on the flat band voltage. Now let us see at what point of time. So, this you can refer to also as VFB, flat band voltage, will be 0 when your phi ms is equals to Q0 prime by Cox prime. What is phi m? This is phi m minus phi s. The contact potential difference between metal and semiconductor will be equals to Q0 prime by Cox prime. What is the effective interface trap charges? See, typically what happens is that the trap charges will vary with position and distance. So, what the best way to do it numerically is that we assume that there is a single value of effective interface trap charges which takes care of the total traps available there, and we refer to that as Q0 prime, right, charge per unit area. So, this is the effect of contact potential, the major changes in the contact potential because of the 4 charges which are available here. This is I thought of ending up this section of the talk with a small numerical problem. You please do it yourself. If time permits, in the next turn we will take up this one, but you need to find the flat band voltage for a p type substrate with a acceptor ion concentration of 9 into 10 to the power 16 per centimeter cube, having a oxide thickness of 100 angstrom, and n type polysilicon gate with Nd 10 into 10 to the power, so 10 to the power 21 centimeter cube per centimeter cube, and the interface trap charges are given as 10 to the power minus 8 coulomb per centimeter square. You have to find. So, flat band will be phi m minus phi s, so phi ms minus Q0 prime by Cox prime. From Tox you can get the value of Cox prime. So, that is done from their case. When you are told to find out phi ms, you will be told to find out the value of Q0 prime, right. So, that Q0 prime can be understood from Nd, right, from the donor trap concentration, and let us see, and if you are using an n type polysilicon gate, you know the value of phi ms from the standard, and from there you can calculate the value of the flat band voltage. Please do it yourself. Later on, if we can come back and explain to you its solution in a much more detailed manner. With this, we have finished with almost everything about CV. Now we will be concentrating for the next half an hour on the capacitance versus voltage characteristics of a device, and we will be looking in the flat band voltage. Basically on the MOS capacitor, these effects, for example, quantum mechanical effects, polysilicon effects, non-uniform doping effects, serial resistance effects, and temperature dependencies. So, this we will be studying in this outline from this course. Now, let us go one by one, that how does the oxide trap actually change the flat band. Now, look at this figure on the right hand side, which is charge distribution in a MOS type capacitor in flat band. In flat band basically means that your phi ms is effectively equals to 0, right, and therefore, the total charge in the oxide, which is this QSS prime, will always be located very close to the oxide layer, oxide silicon dioxide layer, this silicon dioxide silicon layer, towards the oxide side, not towards the semiconductor side, but towards the oxide side most of it will be layer, and obviously the metal will be very near to the metal oxide interface. Now, the equivalent trap charges per unit area, which is QSS prime on the oxide layer, which is just near the silicon dioxide interface, will be composed of 2 parts: the voltage across the oxide layer VOX0 and also the potential across the oxide layer, and if you add those two in flat band must be equals to minus phi ms. So that total VFB is equals to 0. Now if you now apply a external gate bias or a gate voltage, the potential drop in the oxide will also change and the surface potential will also change. So this is what is phi s 0? Phi s 0 is nothing but the surface potential, right, potential at Vg equals to 0 when you do not apply any bias. Now if you apply a bias, then what will happen is that this phi s 0 will show a change, and that change is shown here, which is given as del of phi s. So when you give an external bias, that external bias changes your del Vox and changes your del phi psi, right. So del Vox is what? The final Vox minus the original one when Vg was equals to 0, and phi s minus del phi or phi s 0 gives you the value of del phi s 0, correct. So I am sure that only these two components of the total potential will be responsible for the change in the MOS capacitor in a flat band. Now let us look at the flat band variation due to oxide charges. Now Vg we knew that was equals to Vox plus psi s, the surface potential, plus phi ms, right. Now we can assume that what we can, so if you have charge neutrality across the nature and you have not given an any external bias, and we assume that the charge neutrality is to be maintained, then obviously this must be true, that the total charge on the metal and on the oxide layer, if you add those two together, must be equals to 0, which means effectively that my Qm prime must be equals to minus Qss prime. So they are opposite in nature. Now Qm prime, which is on the metal side, can be given as Qm prime by Cox, Vox, right. Vox can be given by this. In the flat band condition, of course my psi s is equals to 0, because all my energy level diagrams are all flat. It primarily means that my psi s equals to 0, phi ms, and therefore if this is 0, then I can safely write down that my Qs equals to 0, or the surface charge to be equals to 0, and therefore Vg, which is equals to VFB flat band voltage, is phi ms minus Qss by Cox, right. So just Qss minus Cox will be there. What is Qss? The charge on the oxide side will be there, right. This will be there. Now let me explain to you how does a MOS capacitor, maybe I can show you in next slides also later on, but I can show you how. Just let me give one slide here, and we will be actually looking into the depletion thickness band narrowing effect, right. We will come to this later on, but we will be quickly finishing up and giving you an idea about the flat band voltage variations because of the oxide. So we have looked into the flat band variation. Let us now come to a basic concept of capacitance, and we will come to that as we move ahead in this region. Now let us say what we are planning to do is something like this, that the capacitance will be given by dq dv, which means that the rate of change of the charge being accumulated with respect to the applied voltage which you apply will be the capacitive charge, correct. So my capacitive charge C is dq dv, and this is basically an AC small signal charge, right. It is an AC small signal, which primarily means that I have a DC bias which is biasing my device either in accumulation or in inversion or in depletion, and over and above I am riding a AC signal, and this AC signal is charging and discharging the charge carriers within the layer, and because of which there is a capacitance which is being formed, and is basically an AC charge which you see, right. And that is the reason you will have these AC charges in a much more detailed manner. So what we will do as we move along is try to formulate the policy for this charge, capacitive charge. Now let us see what are the various quantization principles. I will just skip and go because at this stage it might not be too much of interest to you, but let us look at the fact. Now when you are shrinking the MOS capacitor by reducing the value of Tox, your Cox actually goes on rising, right. Now as the Tox goes on reducing, since the gate has a better control over the channel, the inversion layer becomes very highly carrier, the number of carriers becomes very large in the inversion layer, and if the dimension of the inversion layer is very small, the transverse direction of the inversion layer is very small, there will be quantization of the inversion energy levels within the this is basically known as quantum confinement, right, and the motion of the carriers perpendicular to the interface. So, if this is the interface, perpendicular to the interface is always moving through a discrete energy level. So, this will happen when you apply an external bias. So, this will not happen when you do not apply external bias so the quantum effects in MOS capacitor is primarily discretization of energy levels which takes place when your dimensions go very low, right, and therefore instead of forming energy level being instead being a continuum, you will actually have discrete energy levels where the potentials will be fixed. Now, let me come to the polysilicon gate depletion, right. Now, in MOS capacitor also you can have polysilicon gate, you can, rather than having a metal gate, you can use polysilicon as the gate, and because it is very much compatible with the silicon process technique, right, and you can have a very stable dielectric surface with the polysilicon, right, strong and dielectric surface, and therefore this is known as polysilicon. Now, if you there is a problem here, however. The problem is in the polysilicon polycrystalline silicon, when you apply a external bias, right, for example a gate voltage, you might actually see a depletion happening just near the polysilicon material, right. So, when that is what is written in the last part of the statement, that when a positive voltage is applied to the gate of an n channel MOS capacitors, the electrons from the polysilicon gate will be repelled away if you are applying a positive gate bias. They will be attracted, I am extremely sorry. So, this will be attracted here, attracted here, and they will be creating a depletion region within the gate material, right. So, if it would have been a pure metal, you would never see such a reaction, but because of the polysilicon gate depletion, polysilicon material, there will be a gate depletion happening within the gate material itself, and that makes the process very difficult. Now, when a positive voltage is applied to the gate of an n channel MOS capacitors, obviously as I discussed with you, the electrons will be attracted and the holes positive charges will be repelled, therefore there will be a depletion region. Now, however, if you do a non-uniform doping within the substrate, there will be many problem areas which will come up because of the fabrication process. What are the various causes of non-uniform doping? Diffusion process, there are annealings are not proper, and there is intentional gradient being introduced in the diffusion process. That is what is known as a non-uniform doping in a system, right. We also have temperature dependencies in a MOS capacitor. I am going a bit in a much more sort of a bird's eye view rather than going internally to it, but please, these are very important also in current technology. The major temperature dependent effects in a MOS capacitor are threshold voltage, carrier mobility and leakage current. So, in leakage current actually increases with temperature increase, threshold voltage increases with decreasing temperature, right, and the carrier mobility actually decreases with increasing temperature. Very simple and straightforward. Why? Because as you increase the temperature, there will be more scattering of the charge carriers because the thermal energy increases, and therefore the mobility starts to decrease. The leakage energy increases because you have large number of EHPs being generated, and that is also the true for threshold voltage. Now, let's come to a point where we will study the CV characteristics for various points. So, if I know how a capacitance versus voltage characteristics work, I will be able to extract the value of the minimum capacitance and maximum capacitance both at accumulation, depletion and inversion, and we can relate that to temperature variation at a later stage, right. So, this is what people have been doing it for a long time. Now, so temperature also has its effect on depletion region widths, right, but they are not for large channel devices not very much dependent. For small channel devices it does depends on it, right. Then the density and activity of the interface trap charges, how much density per unit area, and activity means trapping and detrapping process depends upon the temperature, right. The band gap narrowing happens as the temperature increases. This is also very interesting phenomena, that the band gap Eg which is there between the conduction band and the valence band, that increases or that narrows down as the temperature increases, right. Obviously, the question is therefore raised on the device reliability. So, at high temperature, if the device is stressed, how much the device can actually perform to its best capability is what is known as a device reliability, right. Let me come to the outline of my talk in this lecture, where we will be discussing the CV, current versus voltage characteristics of an ideal MOS device for a MOS capacitor, and then with trap charges how does the current versus voltage characteristics change. Now, as I discussed with you earlier, that the capacitance is given by dq dV, where dq dV basically tells me dq is the magnitude of the differential change in the charge carriers on one plate, and therefore, with application of a voltage onto the gate side, and therefore, you are basically measuring the capacitance when you have an IC signal being applied onto the gate side and you have a DC gate voltage being given. So, there is a DC bias over which the AC signal is superimposed, right, and we get the MOS capacitor device characteristics from here. So, initially we will assume that there are 0 charge trapped in the oxide, and the oxide is perfectly fine, and there are no charge trapped in the oxide semiconductor interface. So, there are no interface trap charges, there are no oxide trap charges, and we will look into the 3 operating conditions: accumulation, depletion and inversion, right. These 3 major operations or conditions we will be looking into in a MOS capacitor. Let us look into the accumulation, and let us, on the right hand side, what is given is basically your capacitance per unit area of MOS capacitor for this accumulation mode, and it is basically, if you look at the oxide layers, which accumulation is. So, accumulation basically means that you are giving, if you want to form an N type MOSFET with a P type substrate, then you have to give a bias which is positive to invert the channel, remember. But if you give a negative potential on the gate side, you are actually accumulating large number of carriers, depletion carriers near the interface, right. So, what you see on the left hand side, that if you give a negative bias, you see a negative charge carriers being developed here, right, because of which a mirror charge is created onto the silicon side, which is giving you a positive charge carriers, right. Actually, you wanted to have a negative charge carriers here, remember. This d of dq and d of dq is primarily coming out because of the additional of dV or addition or of the external voltage. So, the differential change in the charge density will occur at the edge of the oxide, just as in the parallel plate capacitor. So, let me draw a basic band diagram in the accumulation region. So, if in the accumulation region, if you remember, if I have a metal, I have an oxide layer, this is my oxide layer, this is my metal layer, and this is my semiconductor. In the semiconductor, if this is my Fermi level on the metal side, this is my Fermi level on the semiconductor side, right. And if you have this, sorry, I have EI, this is my intrinsic Fermi level, then this is my CI or EV, and this is my EC. Right, and therefore, you see that what you have done is that your EV is now closer to EF, primarily meaning that more of positive nature charges are accumulating on the oxide charge. And since you are giving a positive, you are giving a negative voltage on the metal side, you see the reverse is happening, the voltage is falling down in this sense, right, because it is minus q times, we have already discussed many a times this part. And therefore, the bands are bent in the upward direction, and there will be an accumulation of charge carriers which is positive in nature at this stage, right. So, this is the diagram which you will see when you do an accumulation mode capacitance versus voltage. Let us come to the depletion mode device. Depletion mode device is when you have given a gate voltage, your flat band has actually crossed, and your applied gate voltage is positive for an N channel MOSFET P type substrate, and it is not large to be going to inversion. So, it is between flat band and inversion, you get me point. So, the applied voltage which you are giving is between flat band VFB and VTN, it is between these two, then we have the depletion capacitance. The depletion capacitance, if you look very carefully, since now you are giving a positive bias, you will get a positive metal work function, and therefore you will get a negative on the semiconductor side, which will be given by this xd. Xd is the depletion width which you see, and because of this change of d of dq prime, you will get a change here dq prime here, because of which there will be a extra additional value of your depletion width, which is given by dx. So, if you look very carefully as you move from from metal towards the semiconductor side, I can say that my 1 by C depletion is basically series addition of capacitance gives you 1 by Cox plus 1 by SD prime. What is SD prime? SD prime is this prime which you see, and what is Cox prime is the oxide capacitance. So, if you go from this side to this side, they are basically in series, and therefore you get this addition, and therefore if you look here, this is basically C depletion will be given as Cox CD upon. So, let me make it prime here as well. So, this will be all Cx prime. We already know that Cox prime will be epsilon ox by Tox, and CSD is equals to epsilon x by xd. Xd is what? The depletion thickness, right. So, if you take this depletion thickness and you place this and this back into this equation, I get C prime depletion to be a value which is given by this epsilon ox by Tox plus epsilon ox by T silicate xd, which is very straightforward and simple to look into, which means that your depletion capacitance will increase if you make your xd larger, which means that if a depletion thickness is larger, right, your C depletion will be getting lowered and lowered to a larger extent. As you further increase the value of xd by application of an external bias on the gate side, your C depletion will actually fall down. So, C depletion is inversely proportional to the value of xd. So, if you see in all these discussion, all this formulation which you see, which is I have red colored, my epsilon ox and epsilon silicon and Tox are almost constant. So, these are all fabricated dependent, but xd is basically my bias dependent quantity, right. This is a bias dependent quantity, and since this is bias dependent, as you go on increasing the gate voltage, C depletion will go on lowering, because xd is going on increasing, right, and that is what interesting thing about the depletion capacitance is all about. As you can see here, as the space charge width increases, the total capacitance C prime decreases. This I was telling to you properly. Another point of definition of threshold inversion point is the condition when you reach the maximum xd, and is given by xdt, right. This will yield you the minimum value of C depletion, and that is given by this formulation, that C prime minimum is. So, why is it so? Because this is the place where you have almost the zero inversion charge. After this, the inversion charge starts to shoot up, right, and this condition is to yield the minimum capacitance is given by this formula which you see in front of you. We will take up in the next class post this. Thank you.